So the next term we're going to learn is called the wavefront. The wavefront is an imaginary line on a wave that joins all adjacent points that are in phase. So we're looking at points in phase again. Alright, so first thing you need to know is that this is a definition that needs to be memorized. If you look at handout the learning objectives, one of them says you need to be able to state what is meant by wavefront. Alright, so this is one of those things that you do need to memorize the definition. But of course, we don't just want to talk about memorizing. We want to understand what it means. So adjacent means points beside one another. Alright, so if you look at this situation here, right, this is a pond, and there's a ruler moving up and down that is causing a wave to move from left to right. Okay, so these are waves causing moving left to right. Again, we take a photo. Take a photo of this, and then it's a 3D diagram. So this is a point in time that's paused. Okay. So lines AB and lines CD are examples of a wavefront. Okay. Why? Can you see that all of these points here? These points are all in phase, are they not? Right? They're all at the maximum displacement. Speed is 0, and they're all moving in the same direction, and all of these points are beside each other, right? So if you join all of these points in a straight line, all of these points that are in phase in a straight line, this imaginary line is called a wavefront. All right, same for this, right? All of these points are joined together as well, and of course, when you draw wavefronts, all your wavefront points have to be in phase. Right? So all of these points are actually in phase with these points because they all have the same displacement, speed, and direction. Alright? Because they're all going to be moving down after this. Right? So yeah, remember this moves up and down, right? So all the particles move up and down. So another wavefront along with these two would be here. This would also be a wavefront that we should draw. Alright? If we're drawing all the wavefronts for this. Now let's look at it from a top view to see something else. So looking at it from a top view, it's still the same scenario. The ruler is vibrating up and down. The direction of wave is now moving left to right. Where are the wavefronts? So assuming that these are the peaks, right? So this is a wavefront, this is a wavefront, down here is a wavefront. In fact, it's the exact same scenario, right? So these are the wavefronts. Should I draw them dotted lines? Okay, whatever. So yeah, they're imaginary lines, right? They're not real lines, so I'm just going to draw in dotted lines. Alright, so I want to highlight a couple of properties of wavefronts that are important. This direction moving left to right. What do you notice about the wavefronts? The wavefronts are always perpendicular to the direction of travel of the wave. Right? If the energy is, if it's transferring if it's transferring energy from left to right in a transverse wave, these wavefronts are perpendicular to the direction of travel. Alright? So one thing to take note is that they are perpendicular. Second thing to take note is that what would be the distance? What would be this distance called? If you are sharp, you will realize that if this is a crest and this is a crest, we learned just previously that the distance between two successive crests is called a wavelength, right? And also that a wavelength is the shortest distance between any 2 points in phase, and two successive wavefronts will be the shortest distance. The distance between two successive wavefronts will always be the shortest distance. The shortest distance between two wavefronts will always be the shortest distance between 2 points that are in phase, which is the definition of a wavelength. Okay, so the distance between any two successive wavefronts is always a wavelength. One more thing I want to highlight is that wavefronts don't have to be on the crests. Okay, wavefronts don't have to be on the crests. I could also choose to draw my wavefronts, for example, at the troughs. Do you notice that everything about what a wavefront is still applies, right? All of the points at the troughs are in phase across here. And this wavefront is in phase with this wavefront, which is in phase with this wavefront. So wavefronts don't have to be drawn at the crests. And again, they also don't have to be drawn at the troughs. They can be drawn anywhere as long as they are in phase. Alright, but of course, I think most intuitively, we usually draw them in the crests and the troughs. And even, just when we're looking at real life, when ripples are created, you kind of already naturally see these lines, these ripples that are basically kind of like the wavefronts. Alright? One last thing about wavefronts is that wavefronts don't have to be straight lines. Alright, in this case it's a straight line because a straight dipper produces waves in this way. But if I had a spherical dipper that dipped in the middle of a pond, you'll realize that the ripples kind of move out this way, right? Circular ripples, right? If you look at it, it'll be like this wavefront will represent the peaks. Yep, this one gives you the peaks. Right, so all the crests are joined with these circular wavefronts, and the same things still apply in the sense where the direction of motion of travel is outwards like this, and so the wavefronts are still perpendicular to the direction of the wave. Right, and the same thing applies in the sense where the distance between two wavefronts is still one wavelength. The distance between two successive wavefronts is still one wavelength.